So, hello again and a very warm welcome at A1 Digital. Thank you very much for joining us today. We have a very special webinar coming up, and I'm very happy that we have two very interesting speakers today. It's Keyanoush Razavi, digital business consultant at A1 Digital, who helps our customers with IoT and analytics topics, and Guillem Vidal, who is a senior data scientist at BigML, our partner company, and he's joining us from Spain today. And my name is Philipp König. I'm product marketing manager IoT at A1 Digital in Germany, and your moderator today. And now we'd like to get straight into the topic without any more introductions. I'll hand over to Keyanoush.
Okay, I think you should be able to see my screen.
Yes.
Why I care about digital transformation. I started as an engineer. I worked in Silicon Valley, and my task was to analyze and characterize millions of sensors every day. And it's a daunting task. At Silicon Valley, it's the peak of technological innovation. So you would think, okay, these guys have to figure it out, right? But mostly it looks more like this. So we have the sensors of the machines that we want to characterize or analyze. They send out the data in CSV format most of the time, which I had to collect with C++. It's a coding language to scrape together the data from a lot of local sources, and then putting them a combination of Excel, VBA, and C++ to generate my reports and the charts, and then bringing it all together into PowerPoint for our managers to help them make better decisions. And there are so many things that you can do better before jumping into AI. In these cases, you can start with a database, SQL, you can start using more advanced analytical solutions. Before starting with AI, I would say, also in this case, we have to start exhausting the possibilities of analytics. But what's important here, this way of solving analytical things, it's not scalable. It takes a ton of my time. And to learn more about the data, we would just need 2 of me, or 3 or 5. So there is a limit of how much one person can do. Corresponding to it, as I said before, being AI first means using it last. It's a quote by Will Grannis, CTO at Google, and I'm totally behind it, because there are so many analytical possibilities that we nowadays have to exhaust these capabilities and identify bottlenecks within the processes. As soon as we reach a certain size where one human is not able to advance anymore, even with the most advanced analytical possibilities, we start using AI. And AI is not a separate technology silo. It is something that has to be ingrained in every department. It's nothing that is focused on engineering solely. It is something that we have to use in finance, in HR, in making decisions for the business itself, in engineering itself. So in the future, we will see AI more and more in every department of the company. What it all comes back to is this little chart that I like a lot. It's on the x-axis, we see the number of the advancement of transformation. On the left side, we see the performance or productivity. In a classical sense, the companies, they identified a customer need. They have customer has a problem, and the company creates a solution. It grows bigger. And with it, it creates one department after the other. First HR, and then we need maybe finance, buying department. As the company grows, more and more departments evolve, and they each has their own data silo and models that they use to make decisions. There are communication channels between the departments, but they are limited to the information required, and often exchanging the information is exhausting and time-consuming. So when we transform, we start with a POC, and our goal is to connect departments, helping them make better and faster decisions with the data. For example, connecting engineering with finance, allowing finance to get a faster and more accurate view on their costs and their operating margins without the need of an engineer going through the whole department, collecting information from one area to the other. And this is just the first stage. When we pull it forward, we will connect every department, have a centralized data solution where common libraries are at the core of the company. And we don't look at departments anymore, but we start looking at use cases, at applications. And that's something that had a big shift. This is where we switch from the traditional business to the modern digital business. And Jeff Bezos pretty much initiated it in 2002. He said, any communication within and throughout the company, even external communication, has to be done through service interfaces. No more Excel sheets through mail, no more WeTransfer, no more painstaking collection of data through a local drive or something. It has to be, you have a username, here's the API key, a password, and you have access to this amount of data. Read, write, whatever, mostly read. And this was called the Bezos mandate, and it initiated the change. He was a little bit harsh. He said, whoever doesn't do this will be fired at some, will be fired. Thank you, have a nice day. And this is pretty much the way that we want to go. We want to create this AI factory where AI helps us make better decisions and faster, allowing us humans to focus on what we can do best, solve problems of our customers, and create new applications, create new solutions for the problems. So on top, we have the data at the core of the company, followed by the libraries and machine learning models, and all of that is connected through this layer of APIs with which agile and cross-functional teams can start working together. Finance, HR, and engineering can come together, create a new application to make analysis of HR better. Yeah, their possibilities are endless. And at A1 Digital and Big ML, we are at the core of this transformation. We want to assist our partners asking the right questions, implementing the right solutions, and following them all the way to this final stage of an AI factory, which is always a work in progress. What it is, it's not only that I'm saying it's good, it's good, it's good. It's also numbers show it. It's McKinsey research shows it, but I could also list tons of other research. But I would like to go through a few of these numbers. Digitally enabled industries provide real value, especially in manufacturing. Just reducing the costs of inventory holdings by 15 to 20% by knowing the production patterns and estimating how much is needed throughout the different seasons of the year allows us to reduce these costs, followed by a labor productivity increase because the labor doesn't have to focus on these painstaking jobs that can be automated or by generating better insight on just energy insight, for example. No one has to go and read up a meter. That has to be done automatically through a dashboard in the cloud. Then having better insight through IoT into our machines can lead to a 30 to 50% machine downtime reduction because we can estimate the life cycle of the machine and set up a time where we want to maintain it. And all of this can increase the throughput of the factory up to 10 to 30%. So these are not just numbers, but putting this abstract thing of a digital strategy into a more clearer picture, I would like to go through the work that has to be done to set everything up. First, it makes sense to take at least 2 to 3 months making an upfront analysis of the entire manufacturing network. It's a rewarding job to do this. And there is something called analysis paralysis. And I really hope that this is not the case. And the solution for this is to work in cross-functional teams to analyze the manufacturing network, bring together different departments and different people with different expertises, letting them plan, letting them regularly communicate about the processes of the company, about the processes in the factory, and identify the biggest needs and the biggest business challenges. Our goal is to work value-driven or problem-driven, not solution-driven. Solutions, there are plenty of solutions on the market, but it all starts with the problem someone has. And in the business sense, it is the challenges, the business needs, the current performance challenges, the bottlenecks that we identify in the processes that we have to write down in our upfront analysis. Take the time to do this analysis, ask the right questions. We are also here to help with those questions and going through this analysis of the manufacturing network. And last but not least, these smaller POCs and projects that we run, they have to be ingrained into this wider, bigger picture, this 3 to 5 year vision of the digital strategy journey that the leadership has to maintain. So everyone within the company pulls at the same string in the same direction. And that's important. It all starts by asking the right questions, making clear what the top 3 strategic priorities are within the company. What problems of the customer are we solving? What core services are we delivering? And in this respect, identify the value of digitization for the processes and services that we are delivering and that we're using internally to create the value for our customers. To answer these questions, I have other questions as well. It is asking yourself, how are decisions made within my company and within my network? Are there existing software that each department uses to allow them make better decisions? And identifying the bottlenecks within the company. For example, in my beginning case, it was me having to scrape the data and painstakingly bring everything together into C++ and VBA to create this PowerPoint presentation. And that's not scalable. This is a human bottleneck. If we can reduce it by using a database first and then using automation to analyze the data on a consistent basis, this would all be, this human bottleneck that I am would be reduced. And I can focus on the important work that I would like to do, like designing new sensors, designing new machines, finding customer needs, discussing with them what they want in the future. And this is what I would like to do, and not going through tons and tons of locally stored data. And I would like also to start with one example. It's a low-hanging fruit that most companies are not really taking care of or taking advantage of, and that is monitoring the energy consumption, for example, in a manufacturing plant. This example is out of a paper from an Italian company that manufactures valves and actuators. And they started just monitoring their energy consumption on a very granular basis and bringing them together on a building level. So you have building 1, building 2, building 3 that you see on the left side here. And each building is then separated in the machines, the lights, the ACs that they're using. And just by looking and having this information allows the company and the executives to implement policies that there is accountability behind it to keep the energy saving on. So no one, if someone forgets to turn the AC off, that's not a problem anymore. We can automate this because we can observe it. If someone forgets to shut down the machine, it's no problem anymore. We can see who did it or who didn't do it, or we can just automate this task. Just this simple task of energy insight and monitoring energy consumption allows for a reduction of energy costs by 8%. So it's a low-hanging fruit. Many manufacturers are not making use of this. And it doesn't even end there. Having a bigger production line over different manufacturing hubs or factories would allow to compare production lines. So we collect data of many different machines, and we can separate them in machine 1, 2, 3. And if they're equal in their setup, we can see if their efficiency increases or decreases over time. And we can detect these uneven workloads and start applying new applications, like an anomaly detection if something goes wrong, where a human cannot just do it because the scope of this work, of this task, would be too high to look into this and having this broader view. So we can implement new solutions like this anomaly detection to identify where the bottlenecks and where the efficiency increases are possible within our factory. And I think this is a great place to start transitioning to our partners, BigML, and giving him now the chance to present the anomaly detection case.
Thanks, Keyanoush. So yes, Keyanoush just spoke about a couple examples. I have here to start just a few very high-level examples from manufacturing projects where we use data from sensors and machine learning on top of it. It will be really quick. I mean, very high level. Not. I don't have time to go through the details, but just the first one on the top left, it's about a tunnel boring machine where we, in the end, it's like a moving factory full of sensors everywhere. Those machines are very modern, and there are speed sensors, volume sensors, water flow sensors, and many kind of IoT sensors collecting data in real time. And the goal of the project was just as a proof of concept analysis to analyze the oil temperature races in the engine. And well, by using anomaly detectors and supervised learning on top of it, we managed to prove that materials getting stuck inside the machine were correlated to the oil temperature races in the engine, which was interesting. As a second example, in another kind of factory, in this case, it was about film metallization. In this case, the machines were vaporing metal over plastic film, and the factory process would take half an hour or 45 minutes. And the goal of the project was, with historical data, being able to predict with supervised learning if the outcome of the process was going to be good or bad at different moments of the process. And this would allow the operators to stop the machine or to visualize things to maybe correct the current execution. Another example would be in chemical environment. In this case, we have examples with optimizations of plants. We would do predictive models to predict the material usage and the plant output quality, and group both to optimize the output, so minimize the material usage while maximizing the quality output, and then be able to fulfill recommendations in that sense. This is done with machine supervised learning. And finally, detecting errors in welding in car manufacturing by using anomaly detectors. This way, being able to detect when a weld was erroneous, because otherwise, if it's detected later, it can cost time to correct, and maybe there are other pieces on top of it, so it takes more time, and we might even need to stop the whole process line, which is very costly. So in this case, anomaly detectors were very helpful. Also, in the second case, we use supervised learning here in the film metallization, but nowadays it would be very interesting as well to go forward with it with anomaly detectors. And as you see, I'm speaking a lot about anomaly detection or anomaly detectors, because in general they are very useful in manufacturing use cases. Anomaly detectors are unsupervised machine learning algorithms that look for unusual instances in data sets. The idea is that they provide an anomaly score to each instance, and the highest is the score, the most unusual is the instance. Here we have an example with a few bank transactions, and we highlighted the one in red because it has a much higher amount. It has a unique class within the group, and it has a unique zip code within the group, and that could make it an anomaly. Within that group, that transaction is unusual. And well, that's the idea behind anomaly detectors. In BigML, as an algorithm, we use isolation forests It's the algorithm we use as an anomaly detection. The idea behind it is training decision trees to isolate every instance in the data set by doing random splits through random features. And then if the instances are isolated on top of the tree, they were easy to isolate. And if they are isolated at the bottom of the tree, they are hard to isolate. The greater the depth, the hardest it is to isolate. We would, so as it is an isolation forest, it contains several trees. So there will be many trees in that sense. And at the end, altogether, we combine the depth where instances were isolated to compute an anomaly score. If you do not understand this, don't worry. I mean, let's just think about isolating or searching for unusual instances. Another graphical analogy about the three splits is the ones you see on the left. We have a normal point that requires in this two-dimensional space many splits. So the lines are the splits to isolate that point. And the unusual point on the right requires much less splits. It's another analogy of the decision tree needing less splits. Let's move on to the demo. So my goal here is now to provide a practical demo using BigML, so our machine learning platform. And in that sense, I am going to do a demo over factory failures, so detecting factory failures. The dataset I'm going to use is fake. It has been prepared for demonstration purposes. However, the idea is to use an example that talks to you. So in this case, we can imagine that every row of the dataset is a factory moment. And in this case, we can imagine that it could be for welding, for weld error detection. And so every row could be a weld attempt. And at the right, total right, we can see there's a label, the failure label, that shows whether it was correct or it was a failure. And in general, here there's only one failure. In general, the data set is very, very unbalanced. As features, we would use features taken by sensors in the welding machine or in the factory. And the sensors could be referring to positions, could be referring to current information. There could be noise sensors. We could have also forces, and well, we'll see the data set as well in BigML just in a short moment. Also, keep in mind that there's a URL to the data set in BigML. It's public in the gallery, and BigML is free. So you can create an account for free and use it for free. And you could test and do the demo I'm doing on your own. And I invite you to do so because it's the best way in the end to get used and understand it well. It's very intuitive. This is the BigML dashboard. Here we have a data set, the data set I'm going to use for the demo. This is the data set view. In this case, we see that we have 8,648 instances. And this is our failure field. We have histograms with statistics for all the fields. Here for our failure field, we see that we only have 30 instances. So 30 against 9,000 is quite a very, very unbalanced data set. And obviously with such unbalanced data, using supervised learning wouldn't make sense. So instead of that, we can use anomaly detectors. The idea is training an anomaly detector that where anomalies would match failures. Okay, so here I could set the configuration menu to train an anomaly detector, and the only thing I want to tell the machine before that is that not to use the failure objective. So the goal is matching anomalies with failures, but obviously if we use the failure label, we would be cheating because we wouldn't have it in the real time. So I'm just going to tell the machine it's an ID field, and it will be still displayed in the interface, but not used in the computation. If I click here, it takes a few seconds, and this is how the anomaly detection interface looks. In BigML, we have several learning algorithms implemented, and each of those have their own graphical interface. This is the one from anomaly detectors. By default, we show the top 10 anomalies here on the left. Here, we can see that, for example, the first anomaly on top, we see the anomaly score. So in this case, the anomaly score is the highest. It has a 76%. And we can see the most important fields in our data set, we have sensor fields. So here's the average current, the Z position, the time, and so on. And here we see the importance order. On the right, we would see details about this instance. So these data instances, the most anomalous, and we can see that the average current value is very, very high compared to the other data set distribution, and so on. So we can see that the most anomalous fields for this anomaly instance. And if we go to the bottom, we see, if we go to the bottom, we see that in this case, this top anomaly is not a failure. Okay, and we could spend more time analyzing all those instances. We see that the top 3 anomaly in this case is a failure. We didn't use the failure for the computing, but we keep the label here just to see, and that's why I added as an ID field. And in this case, we see that the instance number 3 is a failure, the number 4 is also a failure, the number 5 is not a failure, and the number 6 is, and I think the last 3 are not. So in this case, by only training an anomaly detector, it managed to keep 3 of our failures in the top 10 anomalies. Okay, that's already, it looks good, but what we would like is seeing setting a score to every instance in our data set, and for that we can do a batch anomaly score and selecting the original data set, which is this one, and this will add a score field at the end of the data set. Like this, we can rename it and then just click on score. And again, this takes a few seconds. I have it already prepared here, and the resulting data set is the original data set with the anomaly score at the end of it. Okay, so we have it here. We can see that in the distribution over our almost 9,000 instances, we have very few scores on top of 0.5. Okay, and our goal here would be to see, okay, do my high anomaly scores match with failures? For that, what I can do is filter and only keep the top scores. We have an interface to transform data. There's filter capabilities, so we can get scores greater than 0.50, 0.5, and then we would get the data set with scores greater than 0.5. We can rename it as well, and then just create that data set. Again, a few seconds, already ready, and here we have there are only 225 instances in the original data set with a score greater than 0.5, and over those 225, if I look into the failures, this one is gathering 27 of my 30 failures I had originally. So it's already getting most of the failures in a much smaller data set. Here, what I can do is plotting the data to see a bit more visually the distribution. So here I can select the score. I could remove that line and select the failure flag. And I could color it by failure flag as well to make it more visible. And then here we can see that where my failures are, how my failures are distributed. Well, we can see that mostly on top of 0.53, for example, we have most of the failures, and obviously not all are failures. So we would have some false positives, but that already managed to isolate a lot of them. Let me go back to the slides. So as a summary here, we had that final distribution of failures by just doing a batch anomaly score. If we decided to move forward with this as a prediction on top of that, we could use a decision threshold of 0.53 and consider that everything on top of that is a suspicious weld, right? Is a suspicious factory moment. Then this would be the resulting confusion matrix. So we would have detected the 27 failures, but we would have 127 false positives. So the resulting precision would be 17.5%, which would say that 1 in every 5 predictions my system would make like this would be correct. And then the good news is that we are catching 27 on over 30 failures. So our system would be catching 90% of the failures, which is quite a lot. So in general, depending on the business, we could see how to use this, but in general, this would be precious feedback for plant operators. So we see this is a workflow that could be useful. So if we train an anomaly detector with historical transactions, historical welds or historical factor reactions, then when there is a new factor reaction or a new weld in that case, we could make an anomaly score prediction. And if the score is higher than our threshold, we chose a threshold of 0.53, then the weld would be suspicious and it could be reviewed by a plant operator. We have seen in the numbers above that this filtering would be very performing in terms of recall, and in terms of precision, 1 in every 5 transactions that, or welds that the operator would supervise would be erroneous. So the numbers are quite good in that sense, and that in general would be helpful for the plant. Another option would be to add automatic, instead of having a human supervisor, add automatic performance on top of that, automatic processes to automate this after the anomaly detection. The idea behind this is that anomaly detectors can be an unsupervised alternative to classifiers when datasets are extremely unbalanced. Here we demoed with failures detection. It is an example. Predictive maintenance could be another example, and in other domains, fraud detection is also very similar, also often approached with very similar method. In general, here the challenging point of this method, in here it was a demo, so we didn't do any feature engineering and everything was already ready. But one of the challenges, the biggest challenges, is preparing or finding the features that will work to match anomalies as failures, right? And another point that is common to those features is that after the anomaly detector is applied, there tend to be quite a lot of false positives. So the original balance of the data set, so the balance of the original data set, which was huge, is reduced, will be drastically reduced. But we should be prepared to at this point here, to still have a few false positives and have either a human supervision or methodology to automate the reduction of those false positives on top of that. So false positives are typical in this approach, according to our experience. And mostly, well, that's the example I wanted to show. I hope it was useful, and I'll pass the word to my colleagues.
Okay, let's wrap it all up. Thank you very much. It was, I mean, I used it, so it's always very interesting to see. Let's get to the conclusion. Why do we do all this? I like this. This is the next chart that I like very much. It is this classical scale versus value of profitability curve, where we have this classical economies of scale U curve, reversed U curve, where we scale our company up by buying more input products or materials and scaling up our output. At some point, it reaches a maximum equilibrium. With digital operating models, we can scale beyond this because these human bottlenecks that we classically have are shifted further and further back in the production chain. So we are able to scale the processes in the business greater than it was possible earlier in traditional businesses. And most companies give up way too early on their journey to digitization. They give up when the classical economies of U curve is already at the peak. And we have to keep in mind that scalable tools that like BigML and Exascale Cloud and our IoT devices are at the core of this transformation that helps to make better decisions, faster decisions, and bring the business forward, allowing people to do what people do best, and that's work with people, identify problems, and be creative. Machine learning has its application, but humans are very creative people. Just a quick word about A1 Digital, last but not least, is we were founded in 2017. Our portfolio consists of IoT and machine learning solutions that you've seen before. BigML is a big partner of us in the machine learning aspect. We have also security and network as a service offerings and our own cloud. That's the Exascale that's situated in Europe. Last but not least, we already serve more than 1,500 customers and have around 200 employees. And our Exascale consists out of at least 4 data centers just in European countries. And what we're trying to do is not replace domain experts. We work with domain experts. We help them ask themselves the right questions to reduce the amount of work that they have to do on a daily basis, like looking through tons of data or scraping data from various sources to provide them other people. So we come in and ask these questions as technology experts. We provide measurement hardware for smart meters, connectivity to transfer the data from point A to point B, provide the platform to visualize the data, and most important, the core of it would be the analytics and machine learning part, where we are an API-first approach with BigML together that allows us to really go into the BIs of the customers and implement ourselves there through the use of API calls. That's where we are situated, and I hope if you have any questions, please reach out to us, to me or to my colleague Guillem. We are very, very happy to help you. And in this respect, we are very happy to provide you a 2-hour free exploration workshop. You can contact me and I will be very happy to bring you through, where we will discuss your ideas and the use cases. I will ask questions to identify business challenges, bottlenecks, and processes that can be improved through digitization. So we are not a solution-driven house, we are a problem-driven house. We try to find the problems and challenges, create a plan for the next steps, and yeah, we will not do any commercial for ourselves. We will eagerly try to help you guys. Thank you very much. I give back to Philip. This is again the perfect transition.
Yes, thank you very much, Keyanoush, and also thank you a lot, Guillem. So what you can see here now is the contact information. I have also pasted the LinkedIn profiles of the two of you. So dear audience, please contact Guillem and Keyanoush directly and get in touch. And although we're quite late, I have to say, we received several questions, and I would like to do a short Q&A session. So maybe, Guillem, maybe you can take this one. How about scaling? So what would be the steps to put in production the project you explained earlier? And thinking further, could it be reused for other manufacturing plants of the same company?
Yeah, so in general, what we do is starting with one project, but it tends to be, so in general, our customers sometimes have multiple plants, and then it is moved on to other plants. With BigML, all the IT and the models are stored in the cloud, so that they could be bigml.com, or we could have private clouds. So in general, we make it easy in terms of, we had the latest MLOps version as well that simplifies that part, and all the deployments and scaling is made easy in that sense. So then after the first example goes well, it's just about training models with other plants' data, because in general plants tend to have different data, and then deploying on other plants as well, and the deployments are made easy thanks to the BigML infrastructure.
Thanks a lot. How would a project where we start measuring energy consumption look like? What's the process? I think, Keyanoush, this one might go to you because you had this topic.
Yeah, absolutely. So first, the Energy Insight, what we do is we go ahead and identify the biggest consumers, the biggest hotspots within factories and within the area of the company, and also correlate them with potential inefficiencies. It's not just about the biggest consumer. It could be a very, very efficient machine. It's also that sometimes smaller users could be highly inefficient and require to be turned off because they're old, because they haven't been maintained. Then we would also continue identifying these energy losses throughout days, weeks, months, years, and couple them with general energy data, but also productivity variables. So it's an interesting case because in this Italian company, they identified that the morning shift was acting more efficient than the midday shift. And in the production value, the productivity variables were the same. So the output was the same, but the input was also the same. Just the energy consumption was not the same. It's a very interesting finding to compare those two and find out where these inefficiencies come from. And then we would continue like identifying in performance indicators that we can couple with those energy measurement data that we have, and then point towards what actions can be done to improve the efficiencies of the factory. This is it's a sub part of this digital strategy. It would be just like an energy improvement strategy. So it is a sub picture of the sub picture, but an important picture, because this is oftentimes for factories a low-hanging fruit that they have to catch quickly. And I think it's also shortly being mandated to start measuring more accurately on a more minuscule basis the energy consumptions of factories. It's just crucial. Having an overview of consumption allows you to just save money and by deploying your policies better. And then you can add more services to those with machine learning, anomaly detection, comparing something where humans would work hours and hours. So it's just the beginning, and I'm getting too enthusiastic about it, but having this database at the bottom allows you to scale up from it, create new applications and services.
Okay, I think that was an excellent ending point also. And it was the last question, so we have reached the end of our webinar. And I say thank you very much to Keyanoush and to Guillem, and of course to our audience. Have a good day. Bye-bye. See you next time.